Hi, this lesson is about the limit laws and different algebraic techniques that we'll use in order to evaluate limits. So let's start with the limit laws. So suppose c is a constant and the limit as x approaches a of f of x as well as the limit as x approaches a of g of x both exist. Then the limit of the sum of f of x and g of x is equal to the limit of each function. So the limit as x approaches a of f of x and the limit plus the limit as x approaches a of g of x. The second limit law is similar. The only difference is that here we're subtracting two functions. So the limit of the difference of two functions is equivalent to the difference of the limits. The third one, when you are taking the limit of a constant c being multiplied by f of x, you can factor that number out. So that's equivalent to c times the limit as x approaches a of f of x. This one is called the product law for limits. The limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. The fifth one is regarding a quotient. So the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, as long as the limit as x approaches a of g of x is not equal to 0. And then the sixth one has like two parts to it because they are related. So the limit as x approaches a of f of x to the nth power is equal to the limit of f of x then raised to the nth power. That makes the computations a lot easier when we actually go to do these using algebra. And the same is true for roots. So the limit as x approaches a of the nth root of f of x, that's the same as taking the limit of f of x and then taking the nth root. And that's as long as n must be a positive integer. So here we'll use some of these limit laws to evaluate. So you're given that the limit as x approaches 3 of f of x equals 4. The limit as x approaches 3 of g of x is negative 2. The limit as x approaches 3 of h of x equals 0. And we're going to use the limit laws to evaluate each of the following. So part A says to evaluate the limit as x approaches 3 of f of x times h of x minus g of x. So we're going to be using limit law number 4 for the product and number 2 for the difference. So we can actually split this up into the limit as x approaches 3 of f of x times the limit as x approaches 3 of h of x minus the limit as x approaches 3 of g of x. And we know what all of these are equal to. All of these limits are given in the original statement. So we just plug in the numbers. That's going to be 4 times 0 minus negative 2. And that gives us a limit value of 2. Okay, so we move on to part B. I have the limit as x approaches 3 of 5 times the square root of f of x. So this time we're going to be using limit law number 3 because of the 5, that's a coefficient, and number 6 because of the radical. So using my limit laws, this could get rewritten as 5 times the limit as x approaches 3 of f of x, and then we take the square root of it. So we know that the limit of f of x is 4. So when you plug in the numbers, you have 5 times square root of 4, but we know square root of 4 is 2. So your limit value is 10. Okay, so now we move on to part C. We need to evaluate the limit as x approaches 3 of negative 7 g of x over h of x. So we're going to apply the third and the fifth limit law. So number 3, the third limit law, is because the -7 is a coefficient to g of x, and number 5 is because we have the quotient of two different functions. So rewriting this in terms of the limit laws, this will be -7, the limit as x approaches 3 of g of x over the limit as x approaches 3 of h of x. But we know that the limit as x approaches 3 of h of x is 0, and this law is only true when the denominator is not equal to 0, and so therefore this limit does not exist. We can't evaluate it using our limit laws. So oftentimes we are using the limit laws as well as the concept of direct substitution, which we talked about in the previous section, in order to evaluate limits. But other times we have to do some algebraic simplification, and sometimes that means factoring or getting a common denominator or using conjugates when we're dealing with radicals in order to simplify it enough so that we could evaluate the limit. So this is an example of where we can go directly to just using direct substitution. And that's because 2, the number that x is approaching, is in the domain of this second degree polynomial. So we can just go ahead and plug it in. And when you plug in the 2, you'll get 2 squared plus 3 times 2, which gives us a value of 10. All right, so let's move on. In this case, we cannot use direct substitution immediately to evaluate the problem, the function, because if I plugged in 2 in here, I would be dividing by 0, and we know that that is undefined. So we're going to see if we can do anything to simplify it first. So we can. Both the numerator and the denominator here are factorable. So when you factor the numerator, you get x plus 4 times x minus 2. When you factor the denominator, you're factoring out the GCF, which is x, which leaves you with x times x minus 2. But when you do that, you can see that the x minus 2's cancel, and I'm left with the limit as x approaches 2 of x plus 4 over x. At this point, I can do direct substitution because plugging in the 2 will no longer result in division by 0. So when I plug in the 2, I get 2 plus 4 divided by 2. That's 6 divided by 2, so I have an answer of 3. So notice that the notation that's being used, notation is really important in mathematics, especially as you're moving up into more complex mathematics. You want to be really careful with it. So I wrote my limit in front all along the path of me simplifying it, and then I stop writing the limit when you actually apply direct substitution. So it's important for you to be careful and make sure you include proper notation. So here's another example of where I can't just apply direct substitution immediately, because if I plug in 2 in for v, I'll be dividing by 0. This time only the numerator is factorable, and when you factor the numerator, you get 4v times v minus 2. So similar to the last example, the v minus 2's cancel, so I'm just left with the limit of, as v approaches 2, of 4v. Again, once you apply direct substitution, you no longer write your limit in front of the function, you're just plugging in the value, and so you get that your limit is equal to 8. So if you recall again from the previous section, this is an example of where the limit exists, it's equals 8, but the function itself does not exist for v equal to 2 because it's not in the domain. All right, so here's another one. Again, it requires some factoring, but we'll have to factor both the numerator and the denominator. So when you factor the numerator, you get x minus 3 times x plus 1, and you can see that my denominator is 3 minus x. 3 minus x and the x minus 3 will not cancel. They are off by a sign. So if you factor out a negative 1 from that denominator, you get negative parentheses x minus 3. And then you can cancel the x minus 3, which means that you will be able to substitute the 3 into this expression. So what you're left with is negative parentheses x plus 1. And when you plug in the 3, you get an answer of negative 4. So again, another example of where the limit exists, but the function does not. This one is also a factoring problem, although it might look a little bit different than the ones we did before because I have an exponential expression where my base is a number, but the numerator is actually the difference of perfect squares. And that's because, remember, when you're multiplying exponential expressions, as long as the base is the same, you add your exponents. So I'm going to break down the 5 to the 2t as 5 to the t and 5 to the t. Again, because 5 to the t times 5 to the t, that's 5 to the t times 5 to the t is 5 to the t plus t, which is 5 to the 2t. That's equals the first term in the numerator. And then plus 1 and minus 1 rounds out the difference of perfect squares that we had in the numerator. The denominator stays the same, but then you can see that I can cross out the 5 to the t minus 1, leaving me with only this limit to evaluate. And when you substitute the 0 in for t, anything to the 0 power will be equal to 1. So 5 to the 0 is equal to 1. And 1 plus 1 equals 2 as your limit value. Okay. So in this next example, I'm going to take a different approach. I'm actually going to simplify this by expanding the numerator and then seeing if there's anything I could cancel. Again, I can't just apply direct substitution because if I plugged in a 0 there, I would be dividing by 0. So always check to see if direct substitution works immediately. When it doesn't, then look for ways to simplify the expression. So that's what I did. I expanded the x plus 7, and that gave me x squared plus 14x plus 49. Then the minus 49 gets brought down. But then you can see that the 49 and the minus 49 cancel each other out. So I'm just left with this expression, x squared plus 14x, but I still can't apply direct substitution. Therefore, I'm going to simplify more. So this becomes, the numerator factors into x times x plus 14. The denominator stays the same, but then the x's cancel out, and I'm left with just the limit as x approaches 0 of x plus 14. When you plug in the 0 right in here, you get a limit value of 14. All right, so here's an example of one with a radical. So oftentimes when you have an expression plus or minus a radical expression in the numerator or the denominator, we can simplify it by multiplying by the conjugate of that expression. So the conjugate means the same two terms, but an opposite sign in the middle. So I'm going to multiply the numerator and the denominator by 4 plus root t. When I do that, I am left with this expression here. I have 4 minus root t times 4 plus root t, and in my denominator, I have and I did a couple of things here. I factored out the t from the 16t minus t squared, and I have the times 4 plus root t there. So do not expand this. It's actually much cleaner if you only expand the numerator because what you're looking for is for something that you can cancel. So when I expand the numerator, when you FOIL it out, you get 16 minus t in the numerator because remember, with conjugates, the outer and inner term cancel out. which then means that the 16 minus t cancel out. So I'm left with the limit as t approaches 16 of 1 over t times 4 plus root t. And at this point, I can apply direct substitution. You plug in the 16 here and in here. You end up multiplying 16 times 8, and that gives me a value of 1 over 128 as your limit. All right, so here we have an absolute value. It's the first time we're seeing an absolute value with our limits. Absolute values need to be treated in a very specific way. We have the limit as t approaches 7 of t minus 7 over the absolute value of t minus 7. So we're going to actually show that the limit does not exist. And remember, the limit does not exist when it either is going to plus or minus infinity, or the left-hand limit and the right-hand limit are different. So it's not because if I plug in 7, I'll be dividing by 0. It can be undefined at the function, and the limit exists. But in this case, the limit will not exist for the main reason that the left-hand limit and the right-hand limit are different. So I wanted to show you here what happens when you plug in numbers close to 7 into your function t minus 7 over absolute value of t minus 7. So when I pick numbers to the left of 7 that are close to 7, like 6.9 and 6.99, and I plug it in here, the numerator will be negative, but the denominator is going to be positive no matter what. So my result is -1 when I'm on the left side of 7. When I'm on the right side of 7, these numbers, 7.1, and then a closer number would be 7.01. When I plug those numbers in here, I get the same value in the numerator and the denominator, so your answer is 1. So those are just examples of what your answer is going to be. It's either going to be -1 or 1, but we need to show that algebraically. So when I approach 7 from the left, that means that the answer inside of here is negative, and the absolute value changes it to positive. That's the same result as putting a minus sign in front of t minus 7. So in other words, if I were to plug in 6.9 in here, I would get the negative of 6.9 minus 7 in the denominator, which makes it positive. Same thing that the absolute value does. So it's just a trick to rewrite the absolute value in a different way without the absolute value so that I can then do this. And that basically leaves me with a constant of -1, same answer we got here. When I approach 7 from the right, on this side, when I'm on the right side of 7, like if I plug in 7.01 or any number to the right of 7, I'm going to get a positive result in the numerator, a positive result in the denominator, and they will be the same numbers, and therefore the ratio is just 1. So I don't need an absolute value at all when I'm on the right side of 7. It's just t minus 7, which means these two cancel out and I have a constant of 1. So since the limit on the left and the limit on the right are not equal, it doesn't satisfy the definition of when a limit exists. It actually does not exist. All right, so the last topic in this section is something called the squeeze theorem. Squeeze theorem is sometimes called the pinch theorem, or it's sometimes called the sandwich theorem. So it depends on the author. The book that we're using calls it squeeze theorem. So it's basically a theorem that states that you can evaluate the limit of a function that's in between or in the middle or sandwiched between two other functions, as long as the limit of the function below it and above it are equal. So that's exactly what this is stating. If f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a or approaching a or possibly equal to a, then if the limit of f of x equals the limit of h of x and they both equal some number L, then you can conclude that the one in the middle, this limit, is also equal to L. So the reason why this is convenient, sorry, is because sometimes g of x, the one in the middle, is difficult to evaluate, but the one below it and above it are easy. So it's like a way of avoiding g of x by working with simpler functions. So we use the squeeze, we're going to use the squeeze theorem to evaluate the limit as x approaches 4 of g of x. And you're told that this is true. 4x minus 9 is less than or equal to g of x, which is less than or equal to this quadratic function. So you already have the first statement that g of x is in between my linear function and my quadratic function. So I don't know anything else about g of x other than it's squeezed between those two functions. So what I need to do is evaluate the limit of the two that are above it and below it. So the limit as x approaches 4 of 4x minus 9, well, that's a linear equation. 4 is in the domain. I can just apply direct substitution. So that gives me a value of 7. I do the same thing for the function that's above it. Again, this is a quadratic functions, all real numbers is in the domain, so I can just apply direct substitution and I again get 7. So the limit of the function below g of x and the limit of the function that's above g of x is equal, which is exactly what this is asking you to show. Then, this is the then part, then we can conclude that the one in the middle has, and this is a typo, the one in the middle has the same limit. So it's also equal to 7. Okay, so here's another example of squeeze theorem. We want to evaluate the limit as x approaches 0 of x squared cosine of 5 over x. So unlike the previous example where I gave you the lower function and the upper function, the ones that are squeezing the one that we're interested in, I didn't give you that, but we can come up with a function based on what we know from trigonometry. So we know from trigonometry that the cosine function oscillates between -1 and 1. Remember, it's got an amplitude of 1, and it goes up and down forever and ever between -1 and 1. So we know that this is true from trigonometry, that -1 is less than or equal to the cosine of 5 over x, which is less than or equal to 1. Now, because this is now an inequality, I can actually multiply the inequality by the piece that's missing. So remember, we're interested in this. So I don't have an x squared in this inequality. So I'm going to multiply all three parts, the -1, the cosine, and the 1, by x squared, which gives me this inequality. -x squared is less than or equal to x squared cosine of 5 over x, which is less than or equal to x squared. That's actually the first condition in your theorem. You have to establish that inequality. So we've done that so far. The second condition is this one right here. We have to prove that the limit of the function that's below the one in the middle, which is this one, and the limit of the one that's above are equal. Okay, so we're going to work on that next. So remember, we're interested in a limit as x approaches 0. So the limit as x approaches 0 of -x squared, I can apply direct substitution, and -0 squared is equal to 0. Same thing here. I have the limit as x approaches 0. I can apply direct substitution into x. So I have 0 squared equals 0. These are equal. And because they are equal, the theorem states that I can then conclude that the one in the middle must also equal 0. So that's it for this lesson. Give the homework a try. Good luck.